Well, my name is Diego Milanes. I am an associate professor in Universidad Nacional de Colombia. And well, I want to thank, of course, Angelo and all organizers of IMAPP for inviting me to give this talk on research in flavor physics sector and a possible proposal for internships. So I will now stop my camera because I have a limited bandwidth. So please, I don't know how have you been doing the seminar, but if you want to interrupt me in the middle, please go ahead. So we don't take doubts until the very end. So just let me start then. Well, so before we start, just let me say a few disclaimers. Even if the talk is called research on the heavy flavor sector, well, heavy flavor is a huge sector. So this talk is quite biased. Number one, an LHCb bias, since I am a member of the LHCb collaboration since quite a long time ago already. So what I will present here is a work that we have been doing in LHCb. The second one, of course, is a personal bias. So I'm showing some part of my current research interest. And what I will be showing here is also a set of preliminary results from ongoing LHCb analysis. And for that, I have to thank mainly 3 students from Universidad Nacional, which are Santiago, Ignacio, and Jonathan, since they provided the plots that I will, most of the plots that I will present here today, but also I want to thank Sergei Barsuk, Antimo Palano, Andrew Usachov, Valeria Shopkovska, and Sevolod Yeroshenko, since they have been also actively participating in this analysis. So, well, I will discuss about 3 main points. First one is towards lepton flavor universality measurements in the R eta C. Second one, a spectroscopy problem on charmed baryons in the D0 proton spectrum. And finally, the search for rare decays, in this case for charmless B sub C decays. So the idea of this, it's going to be, I will try to first of all contextualize the problem, then I will show what we have done so far. All of those 3 analyses are still ongoing, so I'm going to show some preliminary results, and then I will also show some room where to improve it and to go ahead with this analysis. Therefore, there will be the opportunities for internship in the IMAPP in this room for improvement. So let's start with the R eta C measurement. So as you know, lepton universality is a quite hot topic in the last years. Here we can see the couplings of the gauge bosons to the leptons in the framework of the standard model, the photon, the W plus minus, and the Z0 coupling to pair of leptons and coupling to pair of neutrinos. And then we see how those couplings are. And what we can see from a first glance is that these couplings are independent on the type of lepton that we are plugging in here. So we could plug electrons or muons or taus with the corresponding neutrino, and basically the coupling will be exactly the same. And this is what we call lepton flavor universality. The coupling of gauge bosons to the leptons is exactly the same regardless the generation. And this is basically an inherent characteristic of the standard model. And it happens is because of the way the standard model is built. So one way to basically test this very inherent characteristic of the standard model is to look at processes where you have gauge bosons and leptons involved. So what we expect is basically those processes to be exactly the same, except for some phase space and helicity suppression that might arise given the different mass and that we have in the leptons, and of course any deviation from this universality is often used as a proof for new physics effects. Of course, if it doesn't, if let's say if it's not exactly the same and we can prove it, it's because this characteristic of the standard model, well, it's somehow in doubt. So there's room for new physics. So as I mentioned, this lepton flavor universality can be tested in several systems, and in fact, it has been tested in all those systems that I'm showing here, like in the electroweak sector with the Z0 and the W plus decays, in some low energy regime with the kaons decays, and also with the charmonia decays. But of course, it can be tested in the sector of the B decays, in the transitions of the B to S or the transition of the B to C lepton neutrino. One of the advantages of doing this test in this sector is that we have large data samples that have been recorded by the B factory and also by LHCb, and it basically makes that B hadrons can be really studied and be they can say a lot about lepton flavor universality in this case. So let's see first the charge currents. So have a B quark decaying to a C quark basically by emission of a W, and this W will basically couples with a pair of leptons. This is a 3-level process. As it is 3-level, it is expected to have a large branching fraction, but there is one small problem, which is that we have neutrinos in the final state. And so we know for sure that this process will not be fully reconstructed in the detectors that we have nowadays. And with respect to the neutral currents, this is a penguin diagram, goes through a loop process, this B2S transition. And just to, I mean, for you to remember that the B2S cannot go naturally in the standard model, since in the standard model we don't have a flavor change in neutral current, so it has to be through this type of diagram. So it's a loop mediated transition, and this makes that well, it will be a rare decay, and in some cases we will have a fully reconstructible final state, which is good, except if we have a tau lepton here. If we have tau leptons here, well, the tau will decay in emitting neutrinos at certain points, so we will have more or less the same problems here, but well, it's not in all cases. So for these lepton flavor universalities, there is a golden observable, which is called R. For the case of, for both cases, basically for the B2C or B2S transition, it is defined as the branching fraction of the decay of a B hadron to another hadron, let's say in the case of the charged current a C hadron, or in the neutral current strange hadron, where if you see the difference between the branching fraction up and down, it's only the nature of the lepton. So it can be different type of leptons up and down. This is the golden observable. Multiple modes have been experimentally explored. And of course, the more measurements we do here, well, the best will be for the understanding of the standard model properties. So in the case of the B2S, we LHCb collaboration, we have measured RK, RK star, RK short, RPK, and there is a seminar tomorrow about the simultaneous measurement of RK and RK star. And in the case of the B2C, we have the RD, the RD star, it was taken in a simultaneous measurement, the R Jeb psi, and the R lambda C. So this proves basically that not only using mesons but also using variance, this type of measurements can be done. So why it is important, this quantity? Because from the standard model point of view, it is a theoretically clean quantity. So what happens is the hadronic contributions are exactly the same here and here, then they more or less cancel up to a good approximation, and the QD contributions from, well, sorry, I see something sound. Maybe someone raised the hand, or okay, no. Just,
no,
Antonio,
if
just
someone is connected, you can go ahead. I will.
Okay. So yeah, and the QED contributions are well controlled at the percent level. So this quantity from the theoretical point of view is quite clean. And so the tension of these quantities between theory and experiment, plus many others that I'm not discussing here, are what it is considered as Flavour anomalies, which is you might have heard. It's a hot topic nowadays. So let me now focus a little bit in the charge current, which is the B2C transitions. So what it happens in the real life, it's some sort of decay like this, what we have here. And in this case, we have Ws, we have soft gluons, we have a Flavour, heavy hadrons, etc. So we have plenty of different scales happening in this diagram. So it makes us really difficult to compute using one single theory. So we need to go to some effective theories and separate the high momentum from low momentum contributions. And so in this framework of using effective theories, the massive degrees of freedom, which is, for instance, this W, can be absorbed in something that we used to call the Wilson coefficients, which can be computed perturbatively, while the soft momentum or long distance contributions are then described by Fermi-like for fermions operators. As we can see here, for instance, in this red point, we have absorbed this W, and what we have at the end is a 4 fermions operator acting here in this point. So from the effective Hamiltonian point of view, this is written by, well, some sort of constants. Then we have the CKM and the Wilson coefficient here and the operator. This, at least at first order. We have, in this case, more diagrams contributing, which will be reflected as more terms in this Hamiltonian, but this will be the dominant one, and so we will focus on this. So the 4 fermion operator has this shape, looks like this, where PL it's the left-handed projector, and so we can clearly see the axial vector nature of this operator. So when we build the amplitude and we make like the sandwich with the initial and final states, we see that we can factorize this in a leptonic quark, leptonic current, and then we will have an hadronic part, which is this one in red. So this hadronic contribution is computed using form factors. So the amount of form factors that I'm going to need to describe this will depend on the type of hadrons that we have here, the complexity of the Lorentz structure, and also the angular momentum that we will have here. And these form factors are typically an input, and they are taken from lattice QCD, heavy quark expansion. Well, there's many other theories that are used when it is important to say this is used when the bachelor quark is a light quark. So just let me try to go back a little bit, and it is when this quark here, the spectator quark, is a light quark. It's type up or down or even strange. Okay, so let's go for the analysis that we want to do at some point. So what we want to measure is this lepton flavor universality observable, computed in this case for the eta c, and this take us to this whole branching fraction b sub c going to eta c tau nu over b sub c to eta c mu nu. So we can cheat a little bit on this observable, and what we will do is to multiply by 1 in a smart way. So you see this blue thing is the same blue thing that we have here, and the red thing is the same red thing here, but we just rewrite this in a way that it is easier for us. So what we have here in the first factor is something that we will call 1 over r mu. And look at this. This is basically the branching fraction of the b sub c going to eta c mu nu, normalized by the b sub c going to jeb psi mu nu. And the second term is exactly the same thing, but with a tau, right? And the third thing is precisely the lepton flavor universality observable, but for the jeb psi. The one for the jeb psi has been measured by the LHC experiment. So if we want to reach this R eta c, well, we will have to go and measure these two other quantities that we call R mu and R tau. And at the end, this will be something like a double ratio of fractions. As if you see, this is a ratio of fractions. We have a double ratio using basically the jeb psi modes as control modes. So let's start saying that the eta c modes have never been observed. This decay mode has never been observed. This one has never been observed. So the first step towards the determination of R eta c is to measure R mu and R tau. So I will discuss about the measurement of R mu, which is what we're doing now. No, however, the final goal is to contribute to this lepton flavor universality test by extracting R eta c. However, there are several steps that we need to accomplish first, and each of these steps is quite a long step. So to measure this R eta c, just let me mention that we have a couple of experimental aspects. The B sub c production in proton-proton collisions is about a factor 10 to the minus 3 with respect to the B plus 0 mesons. So we have less B sub c as B's in summary. None of the decays that we will explore is fully reconstructed, so that's an additional problem. However, the LHC experiment has shown excellent performance for doing this type of measurements, and with the data sample that we will record in run 3, we might be able to make this first measurement. And from the theoretical aspects, it is also important since the form factor are very difficult to extract. And in this case, it's different as in other cases, because we have in the initial state, the B sub c, the B and the C quarks, both of them being heavy quarks. So the usual methods cannot be extracted. And in this case, cannot be used to extract the form factors. And in this case, the spectator quark is a heavy quark, and there is where all the problem lies. Right, so from a theoretical point of view, it's also quite appealing to make these kind of measurements. And also, as the eta c is a scalar, so we need only 2 form factors, different as the case of the R jeb psi, where the R jeb psi is a vector, the jeb psi is a vector, so we will need more form factors, and we might introduce more hadronic uncertainties in this prediction. Therefore, it is a experimental challenge, and it is a theoretical challenge. It's something that we like a lot. It's very nice to try to pursue this measurement, and if this can be done, it will be an excellent thing from experimental and theoretical point of view. So let's go to the measurement of R mu, which is the first step and the one that we are trying to achieve now. So this ratio of branching fractions can be written as the number of observed decays of each type in LHCb times the corresponding efficiencies, reconstruction efficiencies times the decay mode where we reconstruct the eta C and the JEPSI. In this case, we have chosen to reconstruct them both in the PPR, proton-antiproton final state, and this is done just to reduce uncertainties and to cancel some systematic that can appear in the computation of this ratio of efficiencies. So this number of events are extracted from a fit to the main B sub C variable. The efficiency will be extracted from simulated data. And finally, well, this term will be taken from the PDG. So in this analysis in LHCb is quite simple. So you have the proton-proton collision. Here we produce a B sub C, the B sub C flies, and then the LHCb detector is able to resolve the decay point of the B sub C from the creation point, and the decay can be quite well constructed since we will have three tracks, two of them forming the H harmonia, and the other one will be the muon. So this we will miss this neutrino, but we will have three tracks, enough to construct the vertex, the decay vertex. So this is a preliminary plot of our PPR invariant mass. You can see clearly the presence of the eta C and also the presence of the JEPSI. Now we proceed to make a selection of B sub C candidates, and for this we cannot use the invariant mass of the B sub C because we are missing this neutrino. So we built something called the corrected mass, and this corrected mass is basically the square root of the square mass of the PPR muon system plus the perpendicular momentum of this system square plus this another term with also a perpendicular momentum, and this is built like this, like trying to complete the invariant mass, more or less trying to extrapolate the momentum loss from the neutrino. So this is the variable that we will use to deal with the B sub C. So from simulation, this is the shape that the signal will have, the B sub C to eta C mu nu, in terms of this variable. So it will be a peaking distribution. This variable, it's also, well, I'm showing it here as we can see it from data, and then we will select all these, say, events from Monte Carlo, the events below 5,000 MeV in data, which are the ones that I'm showing here, to make a selection, a multivariate selection, right? Basically to improve the B sub C candidates, the purity of the B sub C candidates. So once this is done, we will perform also charmonium fits in bins of M-core. So basically, in each bin of M-core, we will extract the amount of JEPSI and the amount of eta C that we have. And this is what we see in this plot. Basically, these are bins of M-core. And in each bin of M-core, we make the charmonium fit. And then we extract the JEPSI candidates and also the eta C candidates. But I'm not showing the eta C candidates here. I'm only showing the JEPSI candidates. So this is the number of event of JEPSI, the number of event of JEPSI, for each bin in M-core. And this will let us extract the data, the signal that we are looking for from the data. So we will have several types of contribution here. All of them have a real JEPSI because this is the number of JEPSIs in each bin of M-core. So we will have first some B sub C going to JEPSI mu and several other things, which are peaking backgrounds. This contribution is here in gray, almost imperceptible, but it is there. Now, then we will have some physical background coming from B decays, not necessarily B sub C decays, going to JEPSI mu. These corresponds to this red distribution. This is extracted right now from Monte Carlo. We will have a combinatorial, which is a real GEPSI with a random muon, which is the yellow component, and finally our signal, which is the green component. So we can see that for the GEPSI we have this signal, and of course we will try to do, once we understand this perfectly, we'll try to do the same with the eta C, and in that way we can determine the existence or not of the observation or not of this decay. So this is where we are now. So there's room for many discussions here. First, the exploration of the selection steps, because we are performing right now a two-step selection. First, selecting on the Charmonia, and then selecting on the B sub C. These are two multivariate analyses. Then we want to explore really if this can be done in one single multivariate analysis, just to try to avoid all possible bias that we can introduce. The second one is the characterization of the physical background. This physical background is this red component that we see here. Right now we are extracting it from a cocktail of Monte Carlo, but we have only few events out of this cocktail. So we will need to build a more realistic one using simulated samples, and maybe why not some tools like RapidSim or any other tool that helps us to obtain more events to be able to extract that shape correctly. And finally, the application and understanding of correlations among parameters in a S-plot procedure in the Charmonian fit. Why I'm saying this? Because, well, as I told you, this is extracted from Charmonia fit in beans of M core. But we could easily have applied some S-weight procedure from the fit to Charmonia and extract the same structure. This we did, but then we found that there are quite a few differences, and we blame the correlations of the different parameters, mainly of the background parameters. The background in Charmonia changes in beans of M-core. So this is also something that needs to be studied and understood. So now I think that we can change to the other topic about the spectroscopy. So just let me start saying that in the quark model, basically, and if we focus on SU4, the hadrons will be made of quarks up, down, strange, and charm mainly, and they will create the combination of all these will create an enormous zoo, I like to call it, of different baryons and different states. This is way more broader than the spectroscopy that you can make in the meson systems, of course, because we have one additional quark, and then we can use several symmetries and angular momentum and many other things just to organize all these kind of particles like in multiplets. For instance, I'm showing here some particles with basically the same, the multiplets shown here are particles with the same spin parity. And we know quite well that this model is very good to describe the low energy states, and it starts to fail when you try to compute the excited states of these ground states. But okay, it's still fairly good to compute and to predict the low level states. So how do we do that? Well, we know that baryons are made of 3 quarks, not necessarily different. These baryons are fermions, so they will have an antisymmetric wave function and their exchange of undistinguishable particles. And this wave function can be written as a multiplication of several wave functions. So the first one will have to be to do with the QCD, with the color of the quarks. The second one with the radial form of the wave function. It's a spatial part. Then we will have a angular momentum, so the orbital angular momentum. Then we will have a part related with the spin and also with the flavor of the diquark system. So let's imagine first single charm variance. So I mean variance with only one charm quark as valence quark and two light quarks. So if J is the angular momentum of the whole baryon and small j will be the angular momentum of the diquark pair. So let's try to build the ground states. So we said that okay, it has to have an antisymmetric color. The QCD part has to be antisymmetric. If it is the ground state, the radial part will be symmetric, and also we will have zero orbital angular momentum. So the multiplication of these three will give us some antisymmetric function, but then we will need, as I mentioned here, we will need to know what happened with the spin and the flavor part. So let's see on the diquark part. So we can have several different combinations. So there is a isospin singlet, which is flavor antisymmetric. This will form all type of particles that we call the lambda C. Then we have a isospin triplet, which is flavor symmetric, which form all what we known as sigma sub C. Then there is some isospin 1/2, which can be flavor symmetric and antisymmetric, which are the chi-C. And finally, if the two diquarks are strange, then we will have some isospin singlet, and this is what form the omega sub C baryons. In addition, then we can have both spins of the diquark pointing to the same direction. So you will have J equal 1, and if and that would correspond to a spin symmetric situation, and then we'll have a spin antisymmetric situation with J equal to 0. So the multiplication of these three are antisymmetric, and we need the wave function of the baryon to be antisymmetric. So the only way to build that is these two, or we have flavor antisymmetric and spin antisymmetric, or flavor symmetric and spin symmetric. So this is what we kind of have here. And so let's start with the flavor antisymmetric. So it is the lambda C, isospin singlet, J equals 0. So we will have J equal 1/2 plus. And we also have the chi-C 0 and the chi-C plus, because this chi-C comes in these two modalities, like symmetric and antisymmetric. Now we can see what happened with the flavor symmetric, with the isospin triplet. In this case, if it is flavor symmetric, then we need spin symmetric, and spin symmetric is J equal 1. And in this case, we have two different possibilities. One with the spins of the diquark aligned with the spin of the charm, which makes these 3.5 plus states, or not aligned with the spin of the C quark, which makes this 1.5 plus. So as you see, there is a lot of ground states for these only single charm variants. If we allow these variants to have two charm quarks, then this fauna, it's really extended. But this is only the ground state. So what happened with the excited states? So we can see these again, these the baryon as a three-body system, and in this three-body system, we need additional coordinates to be described. In this case, let's call this lambda and this rho. And then for each lambda and each rho, we can have both radial and orbital excitations. And in addition, we can have more splittings when we add spin-spin and spin-orbit couplings in our model. So this is what it drives us, is to have a really rich and very complex spectroscopy, which is still to be explored. So just let me show you. This is from 2015, but there hasn't been much in this particular case since then. Only a couple of things, but okay. We are looking only to omega C spectrum and sigma C spectrum. Here, the dashed line, like this one here, here behind, this one here, and this one here, are what we know today about different lambda 6 states. And the same for the sigma C. We have this one and this one here. And the rest of lines are computations made from lattice QCD about states that should exist. So as you see from the experimental point of view, there is plenty of room to try to look for all these states. And this is important because this will somehow prove the quark model, right? So, and then we see here also some thresholds, production thresholds, for instance, a D meson and a nucleon, a sigma C and a pion, a sigma C star and a pion, sorry, and sigma C pion. These thresholds are important because we can look for these particles decaying into these decay modes precisely. Well then, so let's focus now in the D0 proton spectrum, D0 proton, which would correspond to this kind of threshold that we have here, like D and a nucleon. So the Bauer experiment back in 2007, they made the E plus E minus, they created this lambda C plus excited states decaying into D0 proton and something else. This was an inclusive production. As you see, it is basically created from the interaction point of the E plus E minus, so there is a lot of background, as we can see here, but we also see a clear observation of two states. First, this one, this peak here, which is the 2880, and this small peak here, which is the 2940. Both of them excited states of the lambda C, which are placed here, here, and here in this table. There is also a small pink, let's call it around 2.85 GeV, but at this point our experiment didn't say much about it. So what happened now with the LHC experiment? Well, there is one analysis, oops, sorry, which is proton-proton going to lambda B 0 and something else, and this lambda B decaying into D0 proton pi with the lambda C plus excited states going into the D0 proton. So this is a completely different production mechanism as this one here, because if you see, this lambda C plus excited state was produced basically along with many other things, but here we are looking this lambda C plus star produced together with a pion, and both of them coming from a lambda B. So there is a coherence in this decay, which is not present here. So here what they do was an amplitude analysis, and in this amplitude analysis, as we have coherent contributions, then there will be an interfere of the non-resonant, or let's call it background non-resonant contributions here with the resonances itself, right? So we see in red the 2880, in this solid blue, the 2940 as our experiment, but there is also a hint from something they call the 2860, as you see here. And this 2860 if you see the peak of this state is below 28.5. So 28.6 is basically here. And what happens is that the interference of this contribution with the definite quantum states non-resonant background makes this shift basically towards the left-hand side of the peak of this resonant state. Good. So now let's see, what are we doing? Well, we are doing basically the same. Just let me show you, well, how it is the decay of this lambda C or the sigma C into the zero proton. It's a completely strong decay. In this case, the excited C baryon goes to a C meson. We are going to build these zero proton pairs, not in the way as it was done here, but in a different way. So what we want is to take them directly from the proton-proton collision. So from this collision, we will create the lambda C excited state, which will immediately decay into a D0 and a proton. The D0 will fly, and we will be able to reconstruct this D0 vertex easily. So we have these 3 tracks in the final state. It's a very easy final state. And we are doing this. This is a similar, actually a similar analysis as the one doing as the one performed in Bavar. So we are producing this lambda C inclusively and not currently with other particle. And we were looking at this only with round 1 data, quite old data already. So we make a very tight selection of the D0 and also the proton. And with D0 and the proton, well, this is the form of the D0. And then with the D0 and this proton, we build the invariant mass. And what we observe is something like this. So here we have what we observe looking at round 1 data. This is basically the same plot as the one above, but with the background, fitted background subtracted. The resonances were described via relativistic Bray-Wigner convoluted with the mass resolution functions. The background, we use basically a simple one-component function. We have used this function in previous analysis involving charm meson spectroscopy, like the reconstruction of D0K, D0 pi, D star 0 pi, D star 0K. And in all those cases, we use a similar background as here. And of course, we can see clearly the 2880 states and the 2940 states, but we also observe some other state near the threshold. And this state is described by something that we call the lambda C 2840, whose parameters are not compatible with what we observe in the lambda C 2860 state found in the inclusive projection. Right, so there is a problem because we don't see a hint of this 2860, but instead we see another thing which is not compatible. And so there is this puzzle between these 2 states. So what can cause this difference? So first thing is that we might be misunderstanding the background composition. Although we have tested this background in, as I told you, in the D star 0K and D star 0 pi inclusive production analysis made by LHCb, but could it be different, the background and also the background near the threshold when you produce baryons rather than mesons? That's basically the question that we would like to solve here. Or there might be some associate production, some remaining associate production of coherent background in this inclusive production that we are applying. So this is something that we don't know. And also the question that we can make, are those 2 different resonances states, maybe? And instead of saying are not compatible, but well, there might be not compatible because they're different, maybe. So this is something that we don't know, and all those questions are open. So here the internships The internship proposals are, first of all, a study from a systematic fitting procedure of possible associated background production and different type of background. So it's basically to try to include associated terms in the background that we are using. As I mentioned before, this is one component background, so we will need to split this one component into a several component background and try to see if we can describe the data with this. Also, there is the improvement of the signal selection by using a multivariate analysis for the background rejections. Of course, as you see here, our sample is mainly background. And so we can perhaps try to make a multivariate selection here to be more aggressive and to try to reduce this amount of background. Maybe if we reduce this amount of background, we can have also signs of what is happening in this region. And finally, to explore the feasibility of run 2 measurements for the DCO proton, but also adding other decay modes as the D+ proton. This double charge will be ideal to look for sigma++, sigma C++ states, and also the D* plus proton with the current available data. And then I don't think I'm going to take a long time explaining this very last analysis. Just let me change of topic again. We're going back to the B sub C, but in this case, trying to look for quite rare decays. So just let me, I mean, I already told and said a few things about the B sub C meson, but let me speak it again. So this is a very interesting system, but it is quite an unknown system. In the B factories, the B sub C system was not reachable, and that makes us, as an LHCb experiment, basically the only place where we can study this system nowadays deeply and with large precision. So it's interesting because it has 2 heavy quarks, similar to what happened to charmonium bottomonium. So one can use some sort of model like non-relativistic QCD and models like that to try to study this system. It is about 1.2 times heavier than the B meson, B with the B hadron and a light quark. And it has a lifetime which is about 3.3 times shorter than the B meson. Although it's shorter, but it can be, in any case, resolved from the primary vertex decay. As I mentioned before, also the production cross-section is about a factor 10 to the minus 3 compared with the other Bs. So it makes it the statistical power of the B sub C is not as good as the one from decays with the B. It can decay weakly by either the transition of the B to some light quark or to the C to some light quark. So if it is a transition of the B to some light quark, it could be, let's say, a C, then you can have decays with the JEPSI and some other light hadron. But then if the B quark is the one that decay, then it will be able to decay to some B meson and a light hadron. Or there is another way. So this B sub C can decay, which is through the annihilation process of the B bar and the C quark. And in addition, almost all the spectroscopy of the excited family of B sub C state is still to be determined experimentally. In this case, in the meson case, it's not as rich and complex as with the baryons, but still you should find a lot of excited states, and so far I think that only one has been found. So there's plenty of things from the experimental point of view to do here. So let's focus our attention in these annihilation diagrams that I was mentioning. So for instance, in the case of the charge B, you can have an annihilation diagram through basically a charge current, and then this charge current will create a pair of of quarks of different flavor, and then we'll have an hadronization process. For instance, this B plus to D plus K0 decay, which is quite weird and hasn't been observed yet. And we can have also annihilation diagrams in neutral decays. In this case, of course, we don't have like an W current because this one is neutral, but then we will have some process like a hard scattering of the B and the D quark, again going to U and C bar, and then having some hadronization. And in this case, for instance, this B0 to G sub SK decay that which has been observed is a pure annihilation diagram. So to know that it is a pure annihilation diagram, the quarks in the final state, the valence quarks in the final state might be different to those in the initial state. Let's say here we have U, B bar, then we have here C, D bar, D, and S bar. So the only way that this can happen is through annihilation. If instead of this hadronization of D, D bar, we will have U, U bar, in this case, we will have a U quark. So there will be another diagrams that takes us from this initial state to the other one. But in this case, for instance, there's nothing else than that this annihilation, at least at first order. So what happens is that these annihilation diagrams are often neglected from the theoretical computations. They are suppressed, and well, there's been some experimental measurements. For instance, this one here, as I told you, it's the upper limit is about 3 times 10 to the minus 6, and this one here has been observed to be something times 10 to the minus 5. It is observed. It is small, but it might not be smaller as people think. There's been the observation of other decays, like B0 to K plus K minus, B sub S0 to pi plus pi minus, B sub 0 to DS minus K plus, which is this one, of course. And this observation suggests that the annihilation term is not as small as we think. Although there are very rare decays, and of course, as all the rare decays, there is always room for talking about new physics here. So this is quite interesting, given this fact. And sometimes the prediction of this process is very difficult because we don't. It's hard to find pure decay, pure annihilation decays as this one here. Mostly in the nature, what we find is that these decays try to compete with other ones, which are the dominant. And so, well, to make computation and theoretical extraction of this is often difficult. Although it's been trying to do with QC factorizations of collinear effective theories, etc. So let's talk about charmless B sub C decay. So B sub C decaying to something which doesn't have the quark charm. And so it can be only through annihilation diagrams. And as the B sub C quark meson is charged, then the only way that we have to this annihilation is through this type of diagrams. So let me show some possible examples that might be interesting to do in LHCb. The first one, there is the decaying to phi k, with the phi decaying into 2 kaons. So we will have 3 kaons in the final state, very easy. The other one is the K star 0 pi. The K star 0 will go to K plus pi minus, and then we will have 3 tracks in the final state, quite easy. And the other one is K star 0 K plus, with this K star 0 bar, sorry, going to K minus pi plus. With this K plus would be a 3 tracks in the final state, quite and easy. And from the theoretical point of view, it can be computed by the 1-3 level annihilation operator only. These decays haven't been observed so far, although in LHCb there has been some searches for it. The first one is the B sub C to PPR pi plus, and also the B sub C to K short K decay. And it just happened that back in 2013, as a side project of a asymmetry study that we were doing, I participated in the first search of this type of decays, B sub C into K short K, at that time using a very small sample of what we had at that point. And of course, we saw nothing because these decays are quite suppressed. But okay, this was the first search for this type of decays. Well, let's focus in this first diagram. Okay. So the theoretical prediction said that the B sub C to 5K, it ranges in something between the branching fraction into 10 to the minus 6 and 10 to the minus 9. So let's take the best case scenario, which is 10 to the minus 6, and then with the run 2 data from LHCb, and assuming that we have an efficiency, reconstruction efficiency of about 1%, we will expect of about 10 of that order of events we will be able to observe in LHCb. Of course, to observe these events, we need to control very well the background under the expected peak. But we could be able to see it if we are in the best case scenario. We will be able to observe already this type of decays with the run to data. As I mentioned before, the topology of the decay is very good, and we can basically use it to make some cleaning of the sample. So we have proton-proton, it collides, then we have the production of the B sub C. These flights, we can resolve this vertex with respect to the primary vertex. Then we will have K plus, K minus, coming from the phi and another K-on. So we have 3 tracks to reconstruct this vertex. So that's quite easy. The strategy for the analysis would be to normalize our measurement with the charge B. So we will use not only as a control mode, but also as normalization, the mode B plus 2 phi K. And this takes us that the observable that we want to measure or to constrain is this one, is the ratio of branching fractions weighted by the ratio of B sub C over BU hadronization factors. And this will be exactly, well, the number of events observed times the efficiency for each case, the reconstruction efficiency. So let's have a first preliminary view to the data. And this is our invariant mass of 2 K-ons, K plus, K minus. This is very preliminary. We see clearly the phi. So taking the phi region, the signal region, and mixing with the addition with the bachelor K-on, we can build the 3 K-ons invariant mass. We can look at the region of the B and also the region of the B sub C. So in the region of the B, we clearly see the B plus 2 phi K signal. And in the region of the B sub C, this gray field region is where we expect to have our signal. I'm not showing it because this is blinded, but this is where we should observe our signal. And then there is something interesting that we apply just a few cuts, cut-based selection, very easy. And we obtain quite a large reduction of the background. As you see, the blue distributions are what we finally, what we have obtained so far using a very simple selection. But in any case, we have here a lot of background, which would not allow us to observe these few events that we expect. Then we need to be more aggressive in this selection and basically control this background up to very, very low levels. And for that, we need to, let's say, go and use all the multivariate selection tools. But this hasn't been done yet. So this is where we are, but is promising because this is what we obtain with a very simple selection. So imagine what if, once we use some neural network thing, that would be way better. So the proposals are, first of all, of course, this development of a multivariate analysis to reduce this combinatorial background. Two levels where we control it, and then we might be able to go for an observation. Then the computation of the ratio of efficiencies from the simulated data, which is basically the computation of this term, which is a key ingredient of this analysis. And then the development of a strategy to determine an upper limit to the observable. So in case that we do not observe it, we will need to pose an upper limit. So we will need to build some confidence interval. So this is about this construction of these confidence intervals. And finally, to explore the feasibility of other B-sub-C decays, as the ones that I show in a couple of slides ago, would be the B-sub-C into K star 0 bar K and K star 0 pi plus. Then the LHCb data, LHCb data is there, and it is almost ready to give it a look. So I think I spoke much that what it was already planned. Angelo, I'm sorry for this. I took more time than the one that you gave me. So let me just mention two things. The summary, first thing is a measurement part of a study of lepton flavor universality. The second one is on spectroscopy. The third one is the search of rare decays. This is a small but quite a wide overview of the different topics that you might find in the heavy flavors sector. And that's it. So thank you very much for your attention. I'm open for all kind of questions that you might have.